So very recently, we had a mass production client who came to us to produce a bunch of electrical enclosures. And they had designed this enclosure to originally be injection molded, but they were exploring 3D printing because quite frankly, it was so cost effective that it could not be ignored. But they came back to us and they had a number of questions and concerns about how to optimize the part for 3D printing. We're going to go through what those concerns were and how to address them, and talk about how you can make it a wall-mounted electrical enclosure and actually take an injection molded design and convert it into a mass-producible 3D printable design. So this was kind of the original design that the client was messing with. It's obviously not theirs, but it was kind of the same basic concept of a wall-mounted block that would have some electronics put inside of there. They had designed it for molding just like this because they wanted it to be a single shot mold. So the mold would come together and clamp over it just like this, and then pull apart, and you would have a much simpler, more cost-effective mold in that regard. So you have the spines coming out the side, the holes cutting out the sides, and then you have the insert right there. And this is a fine design for molding. It is very quick and it's a very efficient way to have it molded. But if you're printing this design, this is very much not helpful. The main issue is that right up here at the top, you have these small little spines that are very frail and can be broken off when they're installing them like that. So that's not really a desirable feature. Also, when you're printing this initial layer, these small spines are not very well adhered to the bed potentially, so they can get knocked over and just ruin the part before the part even gets started. So these are really undesirable. The other issue is that there was a concern about the actual surface finish of it. It looked 3D printed, and even though it's an electrical enclosure, and generally industrial components don't have a large concern about surface finish, it is a concern in this case. So they wanted to get rid of the layer lines and wanted to know if there were ways of doing that. So, okay, we looked at this part and we're like, well, how far are we able to go? How much are we able to modify this design? If they're wanting to stay with the injection molded design, number one, there's nothing we can do about these breaking tabs up there. That's inherent in the design. We cannot make that tougher. We could potentially print it like this, but that messes with the mass production auto ejection, and it also creates an issue with support inside of here, which has more post-processing. You don't want any of that. It needs to be printed like this. One tweak that we suggested was to put small sprues on the first layer. That way that first layer is one continuous circle, and the bases of those small sprues down there are basically solidly connected to the rest of the model, so you eliminate that failure point, and then it's just a couple of snips to knock it loose, or you could even leave those in place and somebody could shove them out in the field. So that would be how to optimize this part if we had to print this injection molded design and push it into 3D printing. But as we've said many times before, trying to 3D print an injection molded design is like trying to put a square peg into a round hole. It's not something that you really want to do. So we decided to throw the kitchen sink at this and just show what the optimum solution would be. And that optimum solution would be this. This, in this case, this addresses all of the needs that the client has and potentially improves it even more. So the first thing that we did is we took those vertical holes so that the part could be slid into 4 screws, and instead made them horizontal. This way they're in the plane of the layers and they're just as strong, and you can still slide the part into its mounting points just as you would before, just turn it 90 degrees. So that solves that issue there. But after that, once we've had those holes, well, we're like, well, we'd like to have them be reinforced. I mean, even though it's in plane, there's still a potential for that cracking. Injection molding can't make really thick features, so let's give them some really thick features. Now this part is exceptionally strong. We use chamfers because chamfers are great for everything, and you're able to add on a lot of structural strength without adding really hardly any material at all. So you get all of this extra rigidity and reliability of the part over time without having to have any sort of concern about its long-term durability. Also, adding in this extra material, this part has a little bit of exposure to some UV, maybe potentially, but since the parts are potted and everything else, giving it that thicker amount of material means that UV degradation cannot permeate the part. It has so much more material to get through before it can actually compromise how the part functions, that thicker feature allows you to use a lower grade material that might not be as UV resistant because you just have more material there to resist it. So we did that, you upgraded the holes. Of course, since we had these holes, we wanted the head of the screw to still have room, so you countersink them there, but again, that geometry is not difficult. Also, side note, make sure that you always fillet the printed base of the part, just a small amount, just like 1 millimeter, because that helps to eliminate any sort of side flow, side extrusion, or in 3D printing, people call it elephant feet. That's a good CAD way of getting rid of that. So we've got that. But we wanted to put a little bit of spice on this model here, and we realized that since this original design had to be in a mold that had to pull apart like this, it could not possibly have any sort of logoing on there, which is kind of damaging to the company because now they can't really promote what their product is. There's no identifier on this except for the sticker itself. And they did want to apply a sticker here, but what if they could just put a logo on there? A logo that is permanent, that will not wear away. They could have any sort of product information on here that's large enough to be communicated. So maybe a serial number could run along the bottom. All of that is doable. So we went ahead and embedded a logo there so that they have all of their branding right there permanently on the part, and they don't have any secondary process where they have to apply a logo to the piece. And again, this would not be moldable because those letters would catch the mold if it was being molded in that direction. So we have taken a single shot mold and turned it into an optimal 3D printed part. But now there's the question of, oh, we don't like the layer lines, we don't want it to look like a 3D printed part. Okay, fine. One of the benefits of 3D printing is that it can apply textures to a part for basically no cost at all. So inside of CAD, you could actually apply like a diamond knurling or any other sort of pattern that you feel like in order to cover over and kind of overpower any sort of the layer lines. But what we did is basically just applied noise to the outside of the part, which roughens it just a little bit and makes it look like it was sprayed with like rhino liner that you would have in the bed of a pickup truck. And that gives the part a really nice rugged look without making it look 3D printed. And again, this would be a very expensive surface finish to do with traditional manufacturing. So we applied that inside of Cura, and then we excluded the logo so that it would be pop just a little bit from that standard texture. And we went ahead and printed it, and this is now the result. So in order to go from a single shot molded piece to a mass producible 3D printed piece that is fully optimal, but still meets all of the product specs as well as strength, durability, and appearance, it's really not that difficult, but we wanted to show this example so that other folks know how to optimize a part for printing. If you have a part that you're looking to have manufactured and you need a design review of it, please send it on over. Our quoting team are all the engineers, so we're able to review the part and give you this type of feedback to say like, could you kind of tweak this, turn that around that kind of way and see how far we can go without compromising what the part has to do, but still making sure it's manufacturable. Because now you get all of the advantages of 3D printing. You don't have the cost of the mold. You have the same per part cost, like in this case, and you get so many other benefits around like logo and surface texture and that kind of thing, and maybe even increased strength with lower grade materials so that you can improve your margins over the lifetime of the part. And then of course there's the long-term benefits. They will always be able to produce these spare parts. The mold doesn't have to be located in a non-US location, and they're able to get the parts in any quantity that they need with mass production printing. So there's a lot of benefits that you can get from this if you can design for the process so that it's reliable to produce them at any time. Hopefully this was helpful. Reach out to us again if you have any sort of parts that you would like to look into having mass produced with 3D printing. On this channel, we talk about how to design and different categories of products that have been made with mass production 3D printing. And let us know down in the comments if there's other topics that you'd like us to cover. Have a great day, everybody.